Okay, so for example, how about a strategy of just remembering everything? You know, just memorizing the whole input sequence in your input string. Well, that's it's rather dumb. It's not very practical, because what if your input string is hugely long? You know, so if you're memorizing huge amounts of data, you're going to need a large number of states, right? And hence, and so the number of possibilities that you could have, you know, the number of possible input strings just exponentially blows up. So, you know, not very practical. So you need to you need to decide, as a designer, you need to decide what information about the problem is crucial, is important, and that you memorize, that you put into memory. Now, you know, that decision is, like I say, an art. Design is an art. There are no real recipes about this sort of thing, but these guidelines are useful, you know, helpful. They help you design. Now, of course, I think one of the reasons why SIPS has given so many questions is to give you lots of scope, lots of possibility to gain experience at being a designer. Right? It's helpful. Okay. So, you know, the crucial, the important, critical information that you need to save, to record, store, memorize. Okay. That's going to depend on the language that you're supposed to be recognizing. Okay, so now, from here on, we're going to be the designer. We're going to start actually designing a concrete automaton, you know, a specific problem, and to give you an idea of, to illustrate these general principles that you've been talking about. Okay, so here's the actual concrete case. We have an alphabet that's just the binary alphabet, so just 0 and 1. So effectively a binary string, you know, just a string of zeros and ones, comes in. That's your input string, right? A binary string. So sigma is just the binary alphabet. Okay, and the language, remember, a language is just the set of all strings that are accepted by the automaton. Now these strings, in this case, what are they? They're strings that have, now it's a binary string, right, because that's your alphabet. These strings all have an odd number of ones. Okay, it's a binary string with zeros and ones, and all it's an infinite. You know, your language now is infinite, right? Because you could have infinitely. Wait a minute, it's a finite automaton. Do you have? That's an interesting question. Do you have a finite amount of time? Subtle questions. Here's an ambiguity. Okay. Well, let's say there's a huge number of possible input binary strings. Okay, let's put it that way. And you're not going to record all of them. You account for every possibility because it's just nuts. So you now know your alphabet. It's the set of strings which have an odd number of ones in that binary string. Okay, that's your alphabet, and you're to find an automaton that detects such strings, accepts such strings, okay, and hence recognizes the whole the alphabet. I've done it again. Recognizes the language. Okay. All right. Okay, now be the automaton yourself. So the zeros and ones come in one at a time. What information do you need to store that's critical Well, the designer in you would say, well, you don't have to store all the information. All you really need to know is what's the number, is it odd or even, of the number of ones that have come in so far. Okay, that's the critical piece of information, right? And so if let's say so far that an even number of ones have come in, well, if another one comes in, well, now you've got an odd number of ones, right? So you don't need to count the actual number of ones, like it's 7 or 38 or 192. That's irrelevant. That's not essential. What is essential is whether the number of ones that have come in so far is even or odd. Okay, that's what's essential. So let's have. So that's the essential information: is the evenness or the oddness of the number of ones so far. Okay, that's crucial information. All right. Now, next step. Once you've decided what the crucial information is that you need to store, to memorize, to put in your automaton, in your states, in other words. Well, now how do you represent that information in terms of states? Okay. Well, now the number that it's come in, number of ones that have come in so far, there are two possibilities, right? It's either even or odd. So let's have two states, Q even and Q odd, that represent that. So Q even, what does that mean? It means that in this context, this problem, this automaton, Q even would mean that so far, reading through the symbols in the input string, the binary string, so far, we have met an even number of ones. And Q odd would be similar. So far we have met an odd number of ones. Okay? Now I've run out of board, but so now you've represented the states of your system, and next thing will be to think about the transitions. When transition rules, your transition function, how to decide when to switch from even to odd or from odd to even. Well, once we've got this far, it's starting to seem a bit obvious now, right? So imagine you're in this state and another 1 comes in. Your current symbol is a 1. Well, then obviously you're no longer in state even. You no longer have an even number of ones, you have an odd number of ones. So if the state is even and a symbol 1 comes in, then you switch to this state, right? Odd. Okay? And similarly, if you're in this state and another 1, your current symbol that you're reading, you being the automaton, and you read a 1, well, now you have an even number of ones in your binary string, input string. So that means you need to switch from odd to even. So your transition rule would be something like, if Q odd, that's a state, and the input symbol is 1, then next state will be Q even. Okay? So you got your transition rules there. Now I'm getting what I said verbally now is what I'll write because I've run out of board. Okay, so I'll finish this off as an example of designing. How many more? So this is the first design example in the text, and we've got one. Just one more. And then we move on into something called regular operations. So regular languages, but what is a regular operation? Okay. All right. So I'll stop there.